Good morning, everyone. So today I am presenting from a Ubuntu system or Linux system. Yeah. So from the drive link, you have to download and extract the material. Uh, so you download, extract those files, and copy them to your run directory. In my case, I've already copied it in my run directory. So does anybody need any help or any instructions in how to copy and download now? I think we've been doing that for the last 2 3 days. So by now everybody might have been, well versed with that. But if still somebody is getting stuck, please let me know. Once you download, it will be in your downloads file. Copy it and then paste it. In the meantime, till you are copying, I will give you an idea of what we have done. So yeah, demo. I have copied it to a folder named demo because I have too many files here. So if you see here, there are multiple cases. But in here, there are two important things. There are two solvers that I have created. One is new scalar transport form and new scalar transport form with two scalars. Okay, so to do this, what I have done is I have modified the scalar transport form. I will open it and I will show you. So I will only tell you basically what are the changes that I have done and how the equation is modeled so that you have an idea. So if I open this C file, .c file, if you see this section over here, this is where we are solving the scalar. So if you see, first term is a transient term, right, where ddt of scalar. The second term is a what you can say advection term, and the third term here Laplacian is a diffusion term, and the last term is a source. So as sir said, if we are modeling source, the quantity of the scalar, um, here what we are trying to do is we are trying to mimic that there is a chemical reaction that is happening. So in the chemical reaction, the concentration of the scalar will decrease with time. That's why if you see there is a minus sign over here, where k is the reaction rate for that scalar. Okay, like what is the reaction rate per second, and so the amount by which the scalar decreases will be governed by this term. So this is what we have added over here. So I'm solving basically this equation. So this is the modification that has been done. Now all of you have got this file with you. I will show you how to compile this file because I have shared one what you can say solver with you, but before using it, you have to make it or compile it. Okay. So now I will show you how to compile this. So first open your terminal. Here I'm opening my terminal directly. For you, you can go ahead and open your Ubuntu from the search. Now once you do this, type run. Okay. I have modified this, which is taking me to the other. I will type okay. Siri. Sorry. Yeah. So I've gone to my correct run folder now. The thing is, I've created two run folders. You don't need to worry. You type run, you will go to the correct folder. Then in that, I have pasted it in demos. I'm going to my demo folder. Now, if I do ls, this is the folder that we have already copied, right? So for you in the run, this folder will be there. Chemical reaction tracer gas. Okay. In that, all the files are there. So go to that. Now, if I do ls, so these are my two solvers, right? So to compile them, first you need to go to those files. So let me compile the first one. So I'm going to the first one. So I'm typing cd new scalar form. And if I do ls over here, there is a make folder. There is create fields.h and there is new transport form.c. So this how to compile it, I've also shared in the in one PDF. If not, I think he will upload it now. So now you need to compile this. To compile, you need to type wmake. So run wmake command and it will compile this. Okay. So please do that and let me know if you have any problem in compiling. Now you are ready to use this solver. Like how you type simple form, pimple form. Now you can type new scalar transport form, and it will run this code. So the step is very simple. You need to go to the folder in which the code is given, and then run the wmake command. Simple wmake. Once this is done, let us also compile the second solver so that we don't have to do it later on. Go back cd dot dot to go back again to the main directory. Now you need to go to the second one, that is cd new scalar transport form 2s. Okay. What I have done, I have gone out of that folder and opened the new folder, that is new scalar transport form 2s. Now I need to compile this as well. So to compile this, again I will run the wmake command. Please do this as well. Okay, this is also done. This is done without any errors. So both the compilation is done. So what I did, I was in the new scalar transport form folder. I typed cd space dot dot to go back, and then cd space new scalar transport form 2s to enter into the new scalar transport form 2s folder. After I enter into that, I run the wmake command. That means now you have compiled both those solvers. Now you will be able to run all the tutorial cases that we have given to you. So this was the first step. So now let me go again back to our main folder. I'll press cd space dot dot. Now the first tutorial that we will be doing is, the first tutorial that we will be doing is the batch reactor. Okay. Now what is a batch reactor? Now in batch reactor, as sir said, we are not simulating any flow. We are just taking one block. So if I open this system, so I'm just demonstrating. Okay. Now I'm not running anything. I'm just showing you. If I open my system file in the block mesh dict, if you see, I have given only one cell by one cell by one cell in all the domain. Okay, it is a 1 meter by 1 meter by 1 meter block, right? And I have given one cell throughout. That means I'm simulating only for one cell, and it is fine. Okay, and I have labeled the walls as upper, lower, left, right, and front and back. Okay, our main aim over here is to because there will be no flow in the batch reactor. There will be no diffusion. There will only be source. So what will happen? We are considering we have injected a tracer and it is reacting. Okay. So its concentration will decrease with time. And the code that we have added, let me show that to you, if you remember that. So it was, so d phi by dt is equal to minus k phi is the equation that we are solving. So can anybody tell me what will be the solution for that? Correct. It will exponentially decay. Okay. Because minus sign shows that it will exponentially decay. So that is what we are trying to check. So the idea is, when we have modified the solver, right, we want to check if each term is getting modeled correctly. So now we are not giving any velocity, we are not giving any diffusion, we are only considering if the source term is working fine. So we should get an exponential decay. So that is what we are going to check. Okay. So if you see over here in my zero folder, my velocity is zero everywhere. Okay. So there is no velocity. Velocity is zero everywhere. So because of this, the advection term will be zero. Okay. Second, my constant transport properties. See, my diffusion term is zero. And my rate of reaction is 1. This rate of reaction, the unit is per second. Okay.
Hello,
Yes.
John. I have one doubt.
Yes.
So if the equation is d phi dt is equal to k, equal to right hand side is a constant term.
Yeah.
But the code you have shown, the
Yeah.
dot C code, so there was ddt term, there was divergence term, Laplacian also.
Yes,
So
correct.
that
So
equation will not changing accordingly.
no, we are not changing. So that's the beauty. We are not changing those equations, right?
Huh.
The main equation remains same. If I
Okay.
give ds1, that is my diffusion, to be 0, right? Already that term becomes 0.
Okay.
Did you
Through
understand?
this thing you were
Yeah,
getting
yeah. So we are giving diffusion as 0. Input. We are giving inputs. So if you put diffusion as 0, that whole term drops off, right? diffusion times the Laplacian term.
Yes.
That
The
term will drop
convective
off
term
because
and the
convective term will drop off because our velocity we have imposed 0. Just now I
Okay.
showed, right? Velocity is
Okay.
0. I can show it to you again. So this is in 0 U folder. So you see my internal field is 0 throughout, and I am not
Okay.
giving any boundary conditions. So everything will be 0. So with
Understood.
time, the flow field is not changing only. So we are giving a 0 flow field. So
Thank you.
because I've given both of them,
Mhm.
advection term will be 0, diffusion term will be 0. Only term will be the DDT term, that is transient term, and the source term. So the solution
Okay.
for this will be an exponential decay. And this KS1 is the rate of reaction. So if you change this, your exponential decay, the rate of exponential decay will change.
Mhm.
Okay. Right now, here with 1, you will get e raised to minus 5. If I put as 2, you will get e raised to minus 25 and so on. Or you can increase the rate of reaction, decrease the rate of reaction by modeling, by changing this value.
This one. And if I change this in the code part, so will that show me any error or
No, it will not show you any error.
any?
But
Okay.
see, you have to write one code, so that is general.
General.
Every time you don't have to go and change the code. The same
Understood.
code you can use for different cases. That is the idea over here.
Okay. Fine. Thank you.
Okay. So for me, I'm using the same solver for out of 9 cases. For all 8 cases, I'm going to be using the same solver. Only these input parameters I'll be changing to switch off diffusion, to switch off
Okay.
maybe advection,
Mhm.
all those things. Okay.
Okay.
So here, one more thing that I wanted to show you is the unit of diffusion is meter square per second, right? By looking at this, and the unit of my rate of reaction is per second, because my scalar is dimensionless. So then this becomes that. And I will also show you the scalar file. So my scalar, this is also something that you have to give, right? So scalar, what I'm saying is inlet at the start, internally it is 1, right? And outside, we are not giving any boundary condition, 0 gradient. So it will calculate automatically, right? So we are starting with 1. And if you see the dimensions of my scalar, it is 0 everywhere. That means it is a dimensionless scalar. Okay, this is important. So here you give the dimension. So now let us run this. To run this in your terminal, I hope now you are in this folder, chemical reaction tracer gas. Okay, if you are in some other folder, you change. You do either cd dot dot or whatever, see where you are, and come to this folder.
Where you define that tracer?
Where have I defined the tracer?
Ah,
Yeah, this scalar one is my tracer. Scalar one, right?
okay.
I have written scalar 1 because later on we are also doing scalar 2, 3. We can add multiple scalars. So the idea is to demonstrate to you with one scalar, and then later on at the end of the session demonstrate to you how we can add 2 or 3 scalars. You can add as many as possible. Okay. Whatever you want for your application, you can
No,
change
I'm
accordingly.
asking from where it is entering. It is entered. The scalar is coming.
So in batch reactor, we have not given any inlet outlet.
Okay.
I think Shar should have given you a diagram. So we have one block, right? In which internally scalar 1 is set to 1. Okay. Now what is our aim? We want to see with time how this concentration will change. So we are not giving any influx from any side.
Okay, understood, sir.
Okay. There is no inlet, there is no outlet, nothing. There is only one volume in which I have added the scalar. So you can think of it like there's a box in which there are say 2 species, and they are reacting, so their concentration will change. Right. So concentration of 1, say if I am looking at A plus B gives you C, something like that. But now, right now, what we are doing, we are looking at only A, right? So to begin with, concentration of A is 1. As the reaction proceeds, its concentration will decrease. And we are saying its concentration is proportional to the rate of reaction times its concentration itself, the rate of change. So it will decay exponentially. We are expecting the concentration to decay in this way. Okay,
Yes,
so
sir.
that is what from 1 to 0 after some time. Okay. From 1 to it will go what you can say, it will asymptotically reach 0. So
Okay.
this is my setup. So now let me just run this. So now go to your batch reactor by typing cd space batch reactor. Okay. So you are in your batch reactor file. Now in your batch reactor, if I do ls, If I do ls, there is 0, all run, constant and system folder. Now here, what you need to do, you need to first run block mesh to generate the mesh. So run block mesh. As you can see, there will be only one cell. Okay, because I've given only one cell. Because to verify this, we don't need to give many cells. There is no other processes are not involved. Has everyone done block mesh?
Yes, sir.
Okay. After that, then you have to run the solver. So our solver is new scalar transport form. So Biraj will type this in the chat and run it. Okay. So I ran it for 10 seconds. To run it, type paraform. So the command is new scalar. I will again show you the command. This command is new scalar transport form. Okay. If you start typing new and S and then press tab, it will automatically take it. After you run that, type paraform. So my paraform will open. Okay. Here in this, the important thing is because we have solved separately for scalar paraform to enable us to see that. Like see if I click apply, I will not see any scalar over here. Okay. By default, paraview will not be able to take that. So what you do is you scroll down over here, right? In the fields, you have to check scalar 1. So again, I will show you. You have to scroll down in the properties tab and select scalar 1. Then scalar 1 will be visible. Now click apply. So now if you go to this VTK blocks, instead of that, you will see scalar 1. So if I click on scalar 1, okay. So at time t equal to 0, my concentration is 1. Okay. As I move ahead, my concentration will decrease. So I'll just scale it for all time. Okay. So now let me come to 0. So what I did is I pressed this second icon over here next to I. So it will scale over all the time step so that you will be able to see the change. So now at t equal to 0, my concentration is 1. Okay. With time, you see the concentration is decreasing. Okay. After certain time, it starts to become blue. Now, if you want to view this, okay, whether my decrease is exponential or no, has everyone been able to do up till here?
So this scalar is consumed in the reactor.
Yes, scalar is getting confused. So here,
So-
what we are doing, we are monitoring only one scalar.
Okay.
Its concentration will decrease. So this is what we are verifying. If I am solving only for one scalar, whether its concentration decreases with time or no, and whether we are getting the correct results. That is what we are doing. Now, once we get that, then we can apply this to any application. Okay. So I hope you are getting this, right? So again, I'll tell you. So the step is, for those who have not been able to do, run paraform. Now in paraform, for the ones who are on Windows, touch result.form, explorer.exe space dot, and then open that file. Now, before applying, scroll down in your properties tab and check the scalar 1. Otherwise, scalar 1 will not be visible over there. So check on scalar 1 and click apply. Now scalar 1 will be visible. Now you can go to VTK blocks and check scalar 1. Okay. Now, and if you are visualizing, see now I will show you. If I just click next, there is no change. But if I click on this eye icon, again, I am not seeing any change in color because it is rescaling to the current, what you can say, current time values, and current time values uniform throughout. So to avoid that, what you can do is use the second feature, that is rescale for all time step. Here with the T, here this rescale option with the T. So rescale for all time step. When you do that, it says that it will take some time, but it's fine. I can rescale. Okay. So now you see my largest concentration is 1 and the smallest concentration is 4.5 E minus 5. Okay. And this I've simulated, I think, for 20 seconds. Yeah. No, this I've simulated for 10 seconds. Okay. So now if you see, if I click on the next frame, my concentration is decreasing with time. Now, in ParaView, how will we verify whether this concentration is exactly decreasing with time or no? So to do that, go to filters, click on data analysis, and there click plot data over time. Once you do that, you need to click apply. So after you click apply, it will generate this. So if you see, the concentration of the scalar is 1 to begin with, and it is decreasing exponentially. So at 1 second, right, if it is e raised to -1, so it should be somewhere around 0.367. I think analytically you all will be able to do this now. So you are seeing an exponential decrease. So did you get it? Now we are verifying that our scalar is working, our code for the source term is working fine.
Okay, can you once
Yeah.
more say about the rescaling part?
Okay. So I will demonstrate what is the problem so you will understand. I'll restart it.
Okay.
So if I run parafoam, what happens is I need to first go and select scalar 1. So this you will have to do every time for all our simulations.
Okay.
Then if I go and select scalar 1 over here, now if you see this my scale on the right over here, right,
Yes,
bottom
yes.
right,
Mm.
it is from 1 to 1.
Yes.
Now if I click on next, it is not changing. So generally what we do, we rescale with this I, right? So we rescale to the visible data range, that is the current data.
Mm.
Rescale to the data at 0.1 seconds. So if I do that, see the values have rescaled. So my value is almost the same and I'm getting blue color. Now if I change, my color is not changing. But I want to see the change in color. So the thing is you should rescale over all time steps. So when you do this, the scale is adjusted so that it will account for maximum and minimum for the whole time duration, right? From 0t to 10 seconds. So when we do this, see our scale is adjusted now. What it was previously 1 to 1, now it is from 1 to 4e minus 5. So with this scale now, if you move ahead in time, you will be able to see a decrease in the concentration as expected. Otherwise, what you will feel is that you are getting some incorrect solution, but no, you are getting the solution. Only thing is the ParaView is not showing it properly. You have to instruct it to show it properly. Okay. After this,
Hello.
yes.
Sir, the graph which is starting in my paragraph is 0.9 concentration, not 1.
Okay. That should not happen. Can you restart that? See, now I'm doing it again in front of you. Go to filters, data analysis. So maybe you might have zoomed in or something like that. By mistake, did you zoom it? So see, go to data analysis, click on plot data over time. Now click apply. The initial concentration is 1, so it should start with 1 only. You see it is starting with 1. So from 1, it will decrease exponentially. Okay. Yeah, that green vertical line, I think it is the, if you see this, right, VTK block, mask or something like that, I think it is that. By default, if your block number is 1, it is plotting that block number also. I don't know why it is plotting that. It should not plot. We should get only scalar 1. So please ignore that green line. Our interest is this black line. It is exponentially decreasing. Okay. So now I hope everybody has done this. So we'll move on to the next. Close this. So our next will be, now that we have verified that our scalar is exponentially decreasing with time. Now let us see if, what is my second case? I think the second case is plug flow. Yeah. So in plug flow, what we are going to give? We are going to give a flow velocity, right? We are going to give a flow velocity and we are going to have the, what you can say, source term as well. So my scalar now will change with time and with space. So here, if you see in the plug flow, there are two folders. One is flow and the other is scalar. So as sir has already mentioned, in the scalar equation, if you have seen also, we are solving only for the scalar, right? But it needs a u velocity because it will get advected by the velocity. So our flow is solved separately. So this is our flow simulation, which I have already done and kept. You can do that. So in that I've solved by the simple form algorithm. So if you see, I have used simple form to solve, and you can see what are the initial conditions that I have given. So there is an inlet in which I have given a velocity of 0.1 meters per second. Okay. Now, is this visible? 0.1 meters per second. Now, what is plug flow? First, I will show you what is plug flow. Then again, otherwise it becomes. So in plug flow, what we are trying to do now, I have made a channel. Now I have made a channel like this. Okay. I hope this is visible. Okay. Now we are giving an inlet velocity of 0.1. Our idea is to see how the concentration of the scalar will change with space, because as it is moving ahead in time, it is also reacting. So its concentration at the inlet is 1, right? As it moves ahead, its concentration will decrease. But we want to monitor concentration at one section, at any one section. So concentration at one section will be uniform if my velocity is uniform throughout. But if I were to give my top and bottom, like these top and bottom as walls, my velocity will not be uniform and it will be parabolic. It will be something like this, right? Because of no slip boundary condition. So one thing you can do is you can give free slip or slip condition, or the other is you can impose a velocity. The velocity over here is 0.1 inlet. So you also impose a velocity to the walls. So the walls are also moving in the flow direction. This is similar to a lid driven cavity, right? So you can impose a velocity to the walls, same velocity, whatever you have given over here, 0.1, 0.1 and 0.1. So with this, what happens? This sort of a velocity profile will not be generated, and your velocity profile at any cross section will be constant. Okay. So now what we are seeing, we are injecting the scalar at with a velocity of 0.1 over here. With 0.1 over here, my domain length is 1 meter. Okay. Now, can you tell me at the outlet, when can I expect the tracer to reach? I've injected the tracer at the inlet, right? With a velocity of 0.1 second, right? For it to 0.1 meter per second, for it to travel 1 meter, it will need, as he said, 10 seconds. Okay, so if I monitor my, what you can say, scalar concentration at the outlet, I should see my scalar reach over there at 10 seconds. That is what we are trying to visualize. If that is happening, that means our advection is also being solved correctly. So do you understand why we are doing this? We are trying to check if our advection is being solved correctly. Yeah, in this what we have given is we'll give a velocity to both the ends, right? So our scalar will move over here. So I have two cases over here. One is RTD uniform, RTD parabolic, and plug flow. So they are kind of similar. So in RTD, what we are going to do, in RTD, we are going to inject with some velocity, right? And we are going to monitor when the scalar reaches at the end. Okay, that will take 10 seconds, as I explained. In the second case, what we are going to do is, with velocity, we are also going to add the source term. So my concentration will be 1 at the inlet. Along the length, this concentration will decrease. And how this concentration will decrease? It will decrease exponentially, right? Because the concentration to start is 1, right? When it travels a distance of 1 second, it should drop to 0.36. Then when it travels a distance of 2 seconds, it should drop further. So this should be the drop, right? So in this is what we are expecting. So let us see the result. Then I will explain the result again if needed. So open plug flow. So what I was trying to share is, in all the simulations from now on, because we are injecting the scalar in a flow field, so we need to establish the flow field first. So what we do, we solve for the flow field by giving velocity. So in my U file over here, I've given an inlet velocity of 0.1. Upper and lower wall are also given velocity of 0.1, right? And pressure boundary condition is outlet 0, inlet 0 gradient, and at the walls fixed. So these are the general boundary conditions for, what you can say, pipe flow. This is a channel. similar. Now we run this simulation, and when we run the simulation, all of you know that there are simulation files that come. So what you need to do is in your last iteration, whatever is the velocity that you got, stable velocity, if you open this, you see it is written. So here all the the velocity field is given over here, right? For all the 2000 internal cells. So this is your velocity, list of velocities. So this file now becomes a initial condition for your scalar, because the scalar has to solve over some velocity. So what you need to do, you need to copy this U file. That I've already done, so you don't need to do that. In case you change, then so you copy this U file, and if you see my scalar 0, that U file is pasted over here. So if I open this, this will be the same U file. So this U is become an initial condition for this scalar, because in the scalar equation you are not solving for U, you are only solving for the transport of scalar, but the scalar is transported because of this velocity field. So that velocity field input is needed. So understand, to do a scalar simulation, you have to do two simulations. One is for the flow, wherein you get the flow established. Now you solve how that flow affects the scalar, or how the scalar moves in the flow. This is done to identify certain features, as sir said. Is there any mixing, right? If I inject scalar at one end, whether it will go down or no. So all those things can be studied with this. So my U is an initial condition, so that has to be copied. So we will be running this plug flow. So in your terminal, you need to type cd space dot dot. Now cd space plug flow. Now in plug flow, there is flow and scalar. So I need to go to scalar. So cd space scalar. Now if I do ls, there will be 0, constant, and system folder. Now you can run. So now you need to have the block mesh file. Other important thing is, between the two files, between scalar and flow, right? The block mesh dict should be the same, because your mesh, the domain, the number of cells, everything should be the same. So whatever block mesh file you are using for the flow, same block mesh file will be for your scalar. So your boundary names, patches, everything should be same. Like upper wall, lower wall, inlet, outlet, all those names also should be the same. Now once you do this, run new scalar transport form. It will start to solve. Okay, I solved for 30 seconds. Now let me run the paraform command. So I've solved and run the paraform command. Now let me scroll down. Here you have to check on the scalar 1 and click apply. Okay, so this is a channel. So we have modified. Earlier it was a square block. Now we have made it a channel. Right. Now if I look at scalar 1, and again I will rescale for all time step. This may take some time. So you see, again we are getting the same. Okay. If you look at the velocity now, let's look at the velocity field. The velocity field is constant throughout, 0.1 meter per second. Okay. Because the top and bottom are also moving at the same velocity, so your velocity is constant throughout. Even the last time step, the velocity will be constant throughout. Now let us go and look at scalar 1. Let me take the smooth one. Okay. So at here, initially, scalar is 1 at the inlet. Now if I solve, that scalar is diffusing with time. Okay. It is diffusing, as well as, because it is reacting, its concentration is decreasing, right? Sorry, here we have not given diffusion. I shouldn't have said diffusion. Here we have given only advection. So if you see our file, diffusion will be 0 over here in plug flow. If I open the, not boundary condition, the properties file, constant transport properties, we have given 0 diffusion and only the, what I can say, reaction. So between this and my batch reactor, the only difference is, now I am solving with the flow. So there is a flow field, right? So at the inlet, the concentration is 1. The concentration is decreasing along the length, right? So if I go to my last time step, this is some steady simulation, that the steady results that I have obtained. Now I want to verify whether I'm getting the same profile. So for this, what I'll do, I'll plot over line. So I will know what is the scalar concentration along this line. if I do plot over line function, and my line will be the x-axis, and then if I click apply, again I will see an exponential decay, right? Because my scalar with a concentration of 1 is now moving ahead. Okay, so it will cover a distance of 0.1 meter. Here, this 0.1 is my time, length. It will cover a distance of 0.1 meter in 1 second, right? And in 1 second, how much should be the, what you can say, reaction? E raised to the power minus 1. So corresponding to this, it will be 0.367, right? That value. So what in my batch reactor, I was getting the exponential decay with time, but now we have imposed the flow. Now we are getting exponential decay with space. Okay, so the concentration at the start is 1. As the reaction is proceeding, scalar is moving ahead, and the reaction is proceeding in time as well. So I'm getting the scalar concentration with space. That means my advection is also working fine. It is advecting the scalar properly. Otherwise, this wouldn't have been proper. Okay. So I will show you the steps of how to do this again. So I hope you have run the simulation, right? After you run the simulation, you have to type parafoam and then scroll down, check scalar 1 and click apply. Now go to VTK blocks and click scalar 1. The rescale over all time steps. This T, second one. Rescale data over all time steps. Then click rescale. It will take some time, but it will rescale. Now, if you run the simulation, you will see it diffusing in space. So the concentration is highest at the inlet because their time is 0. So if T is 0, concentration over there will be 5, initial 5, right? Over here, at some distance, say 0.1 meter, the time taken for the scalar to reach here will be 1 second. So its concentration will decrease appropriately for whatever is the value for 1 second. So this you can verify by plotting over line. So go to plot over line function and then plot over the x-axis, because that is your flow axis. Click apply. So here you see the scalar is decreasing exponentially with space, because the time needed for it to cover that distance of 0.1 meter is 1 second based on the velocity. From the velocity you can compute that. Then time needed for it to reach 0.2 will be 2 seconds. So in 2 seconds it will exponentially decay by e raised to the power minus 2. And if you see, the velocity is constant throughout in the domain 0.1. It is not changing. And this we were able to achieve because along with the inlet, the top and bottom walls also we have made moving.
Sir, I run the same case, but I am not
Yes.
getting the concentration decrease. It is actually increasing from inlet to outlet.
Maximum
Actually, in the
decrease.
previous case also it was increasing. That's why I asked the question how to rescale it and all. It was increasing.
Okay. But still it is increasing.
Yeah, after rescaling also it is increasing. At the exit it is showing 2.4 something.
Okay. Then maybe that wmake command worked for you, right? Properly.
Yeah, maybe the reason. Maybe I run actually the wmake command. I think it worked.
Yeah. Okay, now I understand. Maybe for you, what might be happening is, okay, did you download the recent, from where did you download this case file?
From the drive.
From the drive.
Yes.
So I think you all might have downloaded from 2 different sources. That is the problem. Maybe while Biraj has sent to you. So in one source, I had changed the, what you can say, changed how that source is implemented. Okay.
Sir, after changing the reactant value, again we did the block mesh and same command.
Yes. Yes, block mesh and same command.
Okay.
Okay. But it is always a good practice to always clean the case. Okay. Type foam clean case. I will type the message over here. Foam clean case. In the chat, I've added that. So before you do that, foam clean case so that all your previous simulation results are clean, and then you run block mesh again, and then the command, that is. So what Biraj has shared, download only for the ones for whom it is increasing. So for your case, the problem may be your case over there might be positive and negative. There's some small implementation differences there. Initially, I had implemented with writing k as negative in the code. Then later on, I changed it to changing k directly in the source code itself. The value of k, like positive to negative. So that's why for some it might have become positive and it is increasing with time. So it's a minor change. What is command to run the simulation? Yeah, command to run the simulation is new scalar transport form.
So you first copied the velocity data from the after
Flow
solving it,
simulation.
right?
Yes.
Flow
So
simulation.
I have solved that flow simulation already because we have to run so many cases. So I've solved that flow simulation already and given to you. If you
Okay.
want to modify certain flow parameters, like you want to change the velocity of the flow from 0.1 to 0.2, you have to go to the flow simulation, clean that case, right? By this foam clean case, go to the 0 folder, U folder, change the U velocity from say 0.1 to 0.2. Maybe I will demonstrate it once.
Okay.
Wait.
For this case, this trace is consumed. Suppose there is no reaction is happening, then
Yes.
what will happen? It will be uniformly distributed, right?
Yeah. Then it will just have the same value, right?
Yes.
It will, because what sir said, because it is getting consumed, so
Hmm.
its concentration is decreasing along the flow. If I
Okay.
reduce, I will show you that also. So if I make source as 0, right? If I don't give any source, if I make reaction rate only as 0, then there is no reaction that is happening.
Okay.
And my concentration from inlet to outlet will be
Same.
all one. The whole thing
Okay.
will become red.
Okay.
Is that clear, or do you want me to run that case?
I understand. That's just
Okay. So I will also demonstrate if you want to change the velocity quickly. So you don't need to do that. Just observe this. You all can try this on your own later. So I am in my scalar. So I will go to flow. Right. In my flow, I have all these results. Right. So first I'll clean that case. So clean case. So this command will remove all those files. Now I need to open the U folder. Yeah. Here I will change the velocity from 0.1 to say maybe 0.2. But I will also have to change the velocity of the upper and lower wall to 0.2, 0.2, save it.
Sir, why are we keeping here internal field 0?
That is just an initial value at time t equal to 0. Then the flow will calculate, the calculation will see how the flow develops. So that is the initial guess sort of a thing.
Okay, sir.
So it will develop. So I have saved it. Now I need to run this. So this I have solved in simple form. So the command to run will be, so I need to do block mesh again because I've cleaned it. I've cleaned it, so I need to run block mesh again and then simple form. So this will solve, and say after about 1000 iterations, I will get my final results. So it will more or less be steady. This is what I've observed. Okay. Now if I see the file over here, flow, the new files have been written just now, 1217. Yes. So I will open the last iteration, the velocity from there. I will copy it. Okay. Control C, and I will paste it in my scalar simulation 0. So this is my new initial condition now. While I'm pasting, it will ask replace. I said, okay, replace it. So I have imposed a new velocity. So this is how you have to impose a new velocity. Because you're not imposing velocity only at the inlet, you are imposing the whole velocity field, like whatever is the flow field inside. Now, once I do that, all I need to do is run this. So cd dot cd scalar. Now I need to clean this. Now I need to run block mesh. And then new scalar transport form. So I ran it for 30 seconds. to get a steady simulation or a steady state result. Now if I do parafoam, now can anybody guess what the difference will be between this and the previous one?
To reach the outlet will be less.
Okay. What the distribution will be? Yes. So now I am rescaling it over odd time step. The red region which I was getting here will move a little bit ahead. Okay. Got it. We were getting what we were getting more towards the left will move towards the right because the flow is moving faster. Let's plot it. Plot over the x-axis. Apply. Okay. So see earlier that 0.67 what we were getting for 0.1 second. Now because in the same 1 second, what is the distance traveled by the flow or the scalar? Because it is 0.2 meters per second. So in 1 second it will travel 0.2 meters. So that 0.367 value we will get at 0.2. Okay. You saw the difference between them now. That means our code is working fine. So for the ones for whom it was increasing, you can download the latest file which Biraj has given. Now you will get the same decrease. Okay. So this is done. Now let's move on to the RTD case. RTD case is again straightforward. RTD case is a simple case, same as this, right? In RTD, what we are doing, we are not giving any source. So let's look at the RTD case. So I'll show you the case file for the RTD. RTD. Let's go for RTD. Say uniform. Correct. Let's go to the RTD uniform. So if you see, what is my boundary condition? So for RTD uniform, again, I want a uniform flow field, right? From inlet to outlet. I will get a uniform flow field only if my upper and lower walls are also moving at the same velocity. The velocity that I've given over here is 1 meter per second in this case. Okay, 1 meters per second. Now, whatever flow velocity that I've got, that now I'm adding it into the scalar.
So what is the geometry here?
Geometry is same, exactly same.
Geometry. Okay.
The geometry will not change from now on. Okay. So at the inlet, we have given a value of 1 and everywhere else it is 0 gradient. Internal field initially is 0. Now let's look at what are the properties that we have set for this. So in this, if you look at the properties, both my diffusion and my source is 0. So if both diffusion and source is 0, right? Then what is happening? The scalar is only getting
transported using
transported or convected. The scalar is only getting transported from one transported by convection. There is no diffusion, and its concentration will also not decrease.
Okay.
Earlier, its concentration was decreasing because it was getting consumed by that rate of reaction. Now there is no rate of reaction. It is like injecting an ink, and that ink will not diffuse, but it will just flow in the direction.
But here you are injecting the tracer at the inlet, right?
Yes.
So suppose you want to inject from a particular point in the flow field. So
yeah, from a particular point. I will show you how to inject partially.
Oh yeah.
Right. That I will show you now in the next case. So okay, this case you need to run now. So to run this case, come out of this folder, go to your main folder, cd dot dot. Okay, now I am in my. Wait, let me come to my chemical reaction tracer gas. So now I have to go to RTD uniform. So come to your main folder, that is chemical reaction tracer gas. Type cd RTD uniform. Okay, RTD underscore uniform. And in that, go to the scalar, cd space scalar. Now to run this, again, what you need to do, block mesh, only those two commands, block mesh, and then new scalar transport form. I've ran it for 2 seconds. I don't need much time because it is moving at 1 meters per second. It will reach very quickly, right? So as you all have rightly guessed, what is going to happen is Okay. So my scalar initially is at whatever that is what. You see what is happening? Okay. The scalar is moving ahead. Okay. With time. And after certain time, the whole thing will become red. This is what sir was talking about, right? After the whole thing will become red. That means the scalar will fill the whole fluid. But here, what we are trying to do, here we are trying to say, okay, if I inject the scalar at the inlet and if my velocity is uniform, both the bottom, top velocity is uniform throughout. So how much time will it take for my tracer to reach the outlet? If I inject it over here, my velocity is 1 meters per second. My domain is 1 meter. How much time will it take for the tracer to reach the end?
It is in 1 second.
Yes. Okay. So we can try that. So what we'll do is we'll monitor. Now we have to monitor. So this is something that we'll teach you today. We have to monitor what is the what I can say concentration at the outlet with time. So at the outlet, we will expect the concentration to change from 0 to say whatever at 1 second. So how you can do that? You can do that by maybe unchecking everything in the mesh part in the properties. Uncheck everything and keep only the outlet patch. Okay. So I'm keeping only the outlet patch. Again, I'll repeat in the mesh parts, uncheck everything, check only the outlet part. Now go to filters, data analysis, integrate variables. So you are integrating over the whole this area. Okay. We have done that. Now you can plot this integrated variable with time. Plot data over time and then apply. Okay. So if you see the concentration at the patch is 0 throughout, right? Then suddenly at 1 second, its concentration shifts to 1. So this small this error that is coming, it is due to two things. One is this paraview will extrapolate the data from 0 to 1 over certain region. That is one. And the other maybe because of small, what you can say, the scheme that we are using. If you go for little higher order schemes in advection, then this will become more finer, and you have to refine the mesh even further. Then also this will become finer. So these 2-3 things when you do, so try doing this on your end. Refine the mesh a little bit more, increase it. Okay, this you can try as a assignment. Okay, but I hope this is clear. At the outlet, we are monitoring with time. So when from for time equal to 0 to almost time equal to 1, there is no scalar at the outlet. The scalar reaches the outlet only at time t equal to 1. This is what we are expecting. Okay, because the velocity is constant, so it will advect and it will reach at time t equal to 1.
For some cases, we don't know what is the time taken. So, which means there's some complex flows. So,
Yeah. No, here, see, here, Subin, what we are trying to do is we are trying to verify if our flow physics is working properly, right? If we have modeled correctly. Once we do that, and if everything is working fine, then you can use it for your case, and then you can find actually how much time it is taking. Got it?
Okay.
This is like a validation case. Then you can apply it for your specific case. Say like you can inject tracer in a room where you've given inlet to the room, where Professor Janni was talking about the room simulation, right? You can inject tracer at the inlet of the room. Then you can see when that tracer reaches one corner of the room. So with that, what you will understand is when at what time the fresh air is coming over there, or the air that is coming, how much time it has stayed in the room before it reaches over there. So all these analysis you can do looking at it.
Okay.
But this first, what we are doing for simple cases is trying to see if the model is working fine, if we have modeled everything correctly. Okay. So I will again show you how to do this because I think I went very fast. So please do it with me. I will delete all this. I hope you all have done the simulation. If you have done the simulation, I'll start again. If you have done the simulation is over, type parafoam. or for others, paraview.exe. Okay. Sorry, notepad, touch result.foam, and then notepad.exe and then open that. The same procedure. Once this opens, you need to go scroll down and check the scalar. Now, you have already seen the result. I'll click apply, show you the result again. I'm selecting scalar 1. So my scalar with time is moving ahead and it will occupy the whole domain. Okay. So this is not something that I want, right? This is of no use for me. I also know that the whole scalar is going to occupy. I want to know how much time it took. So to do that, what you will do is in your properties, right? In your properties, scroll down and you see mesh parts. In mesh part, uncheck everything and check only the outlet patch. So now whatever results you'll see only will be for your outlet. So if you do that, if you see everything else is gone, only this outlet patch remains. Okay, please do this. After CD RTD uniform, you need to go to Utsav, you need to do CD space scalar. So you go into the scalar folder to run the scalar simulation. So type CD space scalar. Viraj will reply to you and then run block mesh. That is type block mesh and enter, and then run the simulation command, that is new scalar transport foam. It will run the simulation. Then you have to run the parafoam command. Okay, now I'm going ahead. So after you have this patch, you have to go to filters and then integrate variables, data analysis, and then integrate variables. So you need to integrate because now this patch has a lot of data. Plot over time, you need to compile that into one data per time step. So this integrate variable does that, right? It will integrate for the patch at each time and it will give you when you click apply. So it will integrate over the area. So this will be multiplied by the area. So the exact values will not match. Okay. Now, next, after you do that, it is giving you, see if I move in time, so you see the scalar values are changing. Okay. So it is calculating for every time one scalar value, that is the average scalar value. Now you have to plot this over time. So go to filters, data analysis, and plot data over time. And then click apply. So you'll see a plot like this, where the scalar concentration is 0, and then it becomes +1. It changes at
Here you selected a patch, right? Outlet
yes.
patch. So if I probe at a point, can we do the same probing?
Yeah.
Like at a point, how the concentration is varying with time.
You can do that. I have not tried that. You should be able to do that.
Okay.
You can just try, put a probe point and then try plotting over time.
Okay.
I have taken a patch average. You can monitor data at a point as well. Okay, so this is done. Now, let us go to the next case. The next case is where we are giving a parabolic profile. Okay, that is the more practical case. In practice, the walls will not be moving. The walls will also be stationary, and you will have a no-slip boundary condition. So I will show you those first. So that will be RTD parabolic. Now in RTD parabolic, if I open the flow, 0, you see the boundary condition for U. Here I've given a coded type boundary condition, coded fixed value. So what we are doing, we are specifying the velocity as a function of distance, the location of the cell face. Okay. So this, you have this file. I will quickly tell you what we are doing over here. So we are reading the patch faces, okay, for the inlet. Okay. Now I have created two constants, R and C, where C is the center point. My center point will be at the center of the inlet patch. Okay, and my radius will be half the height of my inlet to give a parabolic profile, right? And what is the maximum velocity? So my velocity will vary from 0 to maximum at the center. So my maximum velocity is 2 for parabolic profile. Now what we are doing, this scalar R, we are reading the phase centers, the phase centers of all cell. So phase center of all cell, it will give you two values, 0 and for 0 and 1. It will be an array of 0 and 1. where 0 will correspond to the x coordinate, 1 will correspond to the y coordinate, and similarly the third one will be correspond to your z coordinate. So we are extracting the y coordinate because we have to vary along the y, right, along the vertical. Now we are creating a velocity vector, wherein the velocity at velocity along the x-axis. That's why I have written it in the place of the first component for velocity. The y and z component of velocity is 0, but my x component of velocity is a function of distance from the center. So I have written it as 1 minus r minus c by r raised to 2. So this will give you a parabolic profile. Okay, so this is how the coded field works. So we have given a parabolic velocity profile. And that's it. Now let me go to the scalar. So you have to now, if you are in the scalar, do cd space dot dot, cd space dot dot again. Now go to cd space rtd underscore parabolic, and then cd space scalar. Flow simulations I've already done, so you don't need to do that. But I've given you the file in case you want to modify the velocity, some parameters. So you have a template with you. Okay, I have done that. Now I will run the blockmesh command and a new scalar transport form. Okay, it has run. Now, can anyone tell me what will be the difference between this case and the previous case? Yeah, so now I will scroll down and click on scalar 1. So can you guess what will happen? Anyone? We have given a parabolic profile instead of a constant profile. Our velocity, average velocity is 1, maximum. So how that parabolic profile will be? At the center it will be 2, at the ends it will be 0. So at the outlet, when will I see it? Will I see it at time t equal to 1 second? Earlier or later?
Later, right?
Okay. Why will I see it later?
Because the volts are not moving.
Okay, I will show the velocity profile. Is this velocity profile correct? At the center it is 2. To verify, I will plot over line. Let me plot over line, plot over the y-axis. Okay, I'm getting a velocity profile like this, where at the ends it is 0, and at the center it is 2. Correct? So my center line velocity is 2. So my center line velocity has increased.
Okay.
So I should sense the scalar earlier. Is this clear?
Yes.
So let me try and show you that scalar 1. So I will rescale for all time step. Okay. Now I am moving. So you see the scalar will diffuse this way now. Is this correct? Because the scalar values which are at the center will be advected more than the scalar values that are at the walls. Okay. You see what is happening? The scalar at the center is getting advected more than the scalar at the walls. And then over time, it starts to develop this way. But if you see, because now that we have given a no slip boundary condition, at the walls, we have a region where yet the scalar has not yet diffused. Because the flow over there is very slow, right? In the boundary layer. This scalar is not penetrating that. So it will take a long time for the flow to reach over there. Okay. But that is not what we are seeing over here. Okay. So the scalar will develop this way for when the walls are stationary. So in this case, the walls are stationary and the velocity profile imposed is a parabolic profile. Now let us do the same thing. Let us uncheck everything and look at only the outlet patch. So if I'm looking at only the outlet patch and I integrate it, filters, data analysis, same thing, integrate variables. so that I get one value for the outlet patch per time. Then I need to go to filters, data analysis, and then plot data over time, and then apply. Okay, we are getting the same thing, but now you will not see a sharp, right? Because as previously seen, it was not what you can say, the scalar was not uniform throughout. Because of that parabolic section, the amount of scalar reached at 0.5 second will be low, and that will increase. So here you see somewhere around 0.5 second is reached when we start to sense the scalar. Okay, this will become more and more accurate if you refine the mesh further, and if you increase and if you use some higher order schemes. Okay, this is what you can also try exploring on your own. Okay, so this is what happens when we use a parabolic profile. Okay, how many more left? I think this is same. You all can try this. So half bore injection is something that we need to do quickly, and then maybe I will demonstrate how the two scalars work. Just let me run this case. So now I will just demonstrate. You all just observe, all these scales files are with you. The steps remain same of what you need to do. Okay. So let me go for half bore without diffusion, without source. I am now directly opening quickly. I'm just demonstrating. Okay. Now you all have this case file. You can try on your own in your whenever you get time. So I will run block mesh, and I will run new scalar output home. So now because I'm using coded value, till it is running, I will show you what I have done over here. So if you see, what is half bore injection? Now I didn't want to inject like for previous cases, right? Inlet we would say uniform value and then say 0, 1, whatever. Now instead of that, what we are giving for inlet, we are giving a coded fixed value. Now that value we are specifying based on the distance. Again, what is my R? R is my center phase distance. Phase center. Y coordinate of my phase center. This means Y coordinate of my phase center. So the Y coordinate of my phase center I am saving in the variable called R, and I am saying if my R is greater than or equal to 0.05, that is half of the what you can say height of the channel. Then I will make the tracer 1, else 0. That means at the bottom from 0 to 0.5, my tracer concentration will be 0. And from 0.05 to 0.1, my tracer concentration will be 1. That means I'm injecting only in the half region. That you will see now. Okay. You have this code with you. If you have any problem in that, you can write to us. It is pretty straightforward. Again, what we are doing is we are extracting what are the phase center values, and based on the phase center values, we are assigning the scalar values to it. So it's straightforward. So now once this is done, let me run Parafoam. Okay. Now I will click on scalar 1, apply. If you see, I will rescale it on function. Okay. Now, okay, my time step was very short. So see what is happening. My scalar is injected only in the top half. Okay, in the bottom half, my scalar concentration is 0. And my scalar is moving only in the top half. This is what sir was talking about, right? Because in this case, if you see my case file, our conditions are, right? My diffusion is 0, my source is 0. That means I am not giving any reaction. So its concentration will remain constant in space. Okay. And because there is no diffusion, it will not move laterally, right? It will only move in the direction of the flow. So for this type of flow, that is laminar flow, where there is no turbulent mixing, whatever you are injecting at the top will remain at the top. It will not come down. Okay. So it will move with time. So even if I increase the time, whatever it is, if I run it even for a full 30 seconds, you see the scalar which is at the top is not coming down. So this is the half bore injection, right? Now same half bore injection, what will happen if I add the diffusion to it? let us look into that. So my half bore injection, but with diffusion. So instead of 0 diffusion, you go half bore and D. Open this file. Now if you see this file, everything else remains same, only I have given one diffusion coefficient, where I've given a very high diffusion of 1e minus 3. Okay. So now let us see what happens to this. Just close this open terminal over here. Okay, and then we have output form. Okay, this is done. Let us type form. Now, if I move ahead in time, you see the difference? Because of high diffusion, that scalar is also coming to the bottom region, where previously we were seeing a very sharp interface between it was totally red on top and totally blue. But this mixing is because of diffusion. So as sir was saying, in the micro reactors, the size is very small. So the diffusivity of liquids, even if it is not large, because the size is small, so it diffuses. And this diffusion is what causes mixing. So here we can see we are kind of replicating that by using high diffusion, even though our sizes are not as small as those for those micro channels and all. But we are simulating, or we are kind of seeing what results to obtain by increasing the diffusion. So if my diffusion were high, it will even mix. It is mixing along the length. You see the concentration going down. Okay, and whatever was here, it is diffusing to the bottommost region. You can try playing around with this by changing the diffusivity values and see how the diffusivity value affects the results. So this is my second case. Now, with source, it is just same. What will happen is along the length, its concentration will decrease. So I will not go to that. I will instead demonstrate the more exciting case of two scalars. Okay, so this with source, both those cases with source are exactly same. The source will what it will do? It will reduce the concentration from inlet to outlet. That's it. You can look into that. I will show you what we have done in this new scalar transport form, two scalars. So the .c file of the previous one that I opened. Now I am opening the .c file for the new one. This is for two, what I can say, two scalars. So as sir said, here, if you see over here, I am solving equation for scalar one, in which I am saying ddt of scalar one plus the convective term plus the Laplacian, that is the diffusive term, is equal to source. Now my rate of reaction is not only dependent upon what is concentration of one scalar, but also concentration of the second one. It is like A plus B. A is my scalar 1, B is my scalar 2. So the reaction will happen only if scalar 1 and scalar 2 both are present. So my rate of reaction, now I'm modeling it as so my source, now I'm modeling it as the rate of reaction times concentration of scalar 1 times concentration of scalar 2. In this, if my scalar 2 is 0, that means there is no scalar 2, then scalar 1's concentration will not change, meaning there will be no reaction. Okay. So here you see minus, that means scalar 1's concentration will decrease when both those scalar 1 and scalar 2 are there. Similarly, for scalar 2, everything else remains same, and scalar 2's concentration will decrease if both scalar 1 and scalar 2 are present. But scalar 3 is my product. Okay. Difference between this and this is the source term. If you see, my concentration of scalar 3 will increase if both scalar 1 and scalar 2 are present by the same amount by which this is decreasing. Okay. So whatever is minus over here, this will be plus. So it will increase accordingly. Now we are solving for three equations. So as I've added three scalars over here, initially I showed you how to add one scalar. Showed means I just showed how I've added one scalar. And here I'm showing you how I've added three scalars. Now let's look at the results with this. We have already compiled this. So it is in multiple scalars. So the setup file for this is in multiple scalars. So if I open that, flow is already done. So let us look at the scalar. Now here what I've done is the diffusivity was, let me see, our diffusivity was low. I have given some rate of reaction. Let me run this and we can change and run it again. Okay, this file I'll run. Okay. So block mesh. It is in opening. Block mesh. Then my solver is new scalar transport form 2s. Remember, when you have to use multiple scalar, when you have to run this file, the solver name is different. So the solver name is new scalar transport form 2s. Okay. Okay. Let it run. I will also show you the setup. Till then. Okay. So till it is running, I'll show you the setup. So what is the setup like? So if you look at scalar one is injected wherever R is greater than 0.05. That means scalar one is injected at the top half section. Okay. Scalar 2 is injected where R is between 0 and 0.05. That means it is injected in the bottom half. So that means scalar 1 is flowing at the top, scalar 2 is flowing at the bottom. If there is no diffusion, will they react?
No.
Because they are flowing separately, there is no mixing, right? So we will look at two cases where first wherein the K value or the diffusivity value is very low, and for the other where we increase the diffusivity value. Okay. And if you look at scalar 3, scalar 3 at the inlet is 0. That means there is no products at the inlet. At the inlet, scalar 1 and scalar 2 both are 1 in one half, and for scalar 2 at the bottom half. But scalar 3, that is the concentration, is 0 at the inlet. So this is how we have specified, because there will be no products at the inlet to begin with. Now let us see. We have run the case. Now let me run paraboom. We go to, I have to check scalar 1, 2, 3 all to see all of them. Let us see scalar 1. Okay. Take something. Just hold on. Okay. So if you see, scalar 1 is flowing only at the top. Okay, slowly. Okay. What about scalar 2? Similarly, let me go to initial tension. Scalar 2 will flow only at the bottom. I have to rescale this again. This is the glitch in ParaView, so you have to rescale it because it is scaling according to this. Yeah. So it is scaling. Sorry, scalar 2 is moving only at the bottom. Okay. So what will happen now to scalar 3? Scalar 3 is there. You see that there is no scalar 3 forming, or there is very minimal. The values that you are seeing is e raised to the power -7. So whatever this some little bit amount that you are seeing, it is because of the interpolation error in ParaView, and also because of maybe some problem in your schemes. Like if you have to use a little bit higher order schemes, but these are negligible values, like e raised to the power -7. Okay. Now this is for very low diffusion. That is, scalar 3 is not formed at all. Let us go and just change the diffusion coefficient. That diffusion coefficient is available in your constant. So as soon as I give some amount of diffusion, right, for both scalar, yeah, here for 1 and 2, I had given 0. That's why it was not diffusing. Okay. As soon as I give some diffusion, I will not give very high diffusion, but say I give something like 1e minus 5. Okay. If I give this and I save it. So what I have changed, only that rate of reaction I have increased to 2, so it will react faster. Now I need to clean this case. Yes, and then I will run block mesh. and then use scalar transport form to scalar. It will take a minute to run. Yeah. Home. Also, you can increase the you can decrease the runtime by running it in parallel. I have not done that here. We have taught you how to run in parallel by using decompose utility. Apply. And yeah, here, let me go to scalar 1. Okay. So if you see what is happening, scalar 1 is moving. Did I clean the key? Okay. What about my scalar 2? Yeah, scalar 2 is also moving, and there is some amount of diffusion at the interface. Now let us look at what is scalar 3. Okay. So you see scalar 3 is getting generated as it is moving ahead. This you can increase the diffusivity further by maybe an order of magnitude, and you will see this red spreading more. This is like maybe two things are coming in, they are reacting and they are creating products. So as the distance increases, the product's concentration will increase. So the phi value of the product will increase. So this is what you're getting. You can run this by increasing your diffusivity, this value. Yeah. This value, you can increase it maybe by maybe something like -4 and -4, and then see the results for yourself. Okay. So this is something that you can try. I think we can break for lunch now. It is almost 1 o'clock.